Welcome to Logical Verification 2020 to 2021. This video is about Chapter 12, Section 5. We're going to look at a few other container types for finite collections, similar to lists. So in the previous chapters, we've seen a lot of lists, but there are also nice other data types that we can use for finite collections. So in a list, it matters both how often an element occurs in the list as well as the order they appear in. So the list 1, 2 is not the same as the list 2, 1. And similarly, the list containing the element 1 is different from the list containing the element 1 and 1. Of course, these are lists. So in this section, we're going to look at two other container types which do not make this distinction. For example, multisets are lists where you ignore the order. So in the multiset, we have the multiset consisting of the elements 2, 3, and 4 is the same as the multiset containing the elements in the opposite order. Like the permutation of the elements, the order does not matter in a multiset. However, whether an element appears more than once, so it's duplicated or not, still matters. So here we have the example. The multiset containing the elements 2, 3, 3, and 4 is different from the multiset containing only 2, 3, and 4. And then if we go one step further, we can also ignore the order. We can just, the only important thing is whether an element is contained in the container or not. This is a finset, a finite set. And a finite set then ignores both whether an element is duplicated or not, as well as the order. The syntax that we use to write multisets and finsets is different from lists, partly in order to indicate that these are different things and do not respect the order of the elements. So they're written using curly braces. Notation works for both multisets and finsets. It also works for your own type. You just need to, so it's based on two type classes, on the hasMTC type class, which gives you the empty set. But of course, this also works for arbitrary sets or finsets. And the other operation that you need to implement on your own type if you want to have this nice curly brace notation is the insert function, which is the hasInsert type class, and it has this type here, the insert function. Okay, as long as you have those two operations, you get this notation with the curly braces for free. And we see one more thing here in these examples, this stack trivial term here. So it's actually not a function by itself. It is a notation for a very weird lemma here that is called of as true. And this can be used to prove any small decidable goal that doesn't have any variables in it. So for example, if we had an n here, then this would no longer work, even though the multisets are always different. So stack trivial really only works if you do not have variables in your goal and it's small and the goal is also decidable. Decidable, you've already seen this. This is the same notion that we also have for if then else statements. Okay, so these are the three nice container types, and you can use them if you don't want to make it, if you want to make clear that there is no distinction based on the order of the elements or whether an element occurs duplicated in a list. If you here execute code in the Ling virtual machine using eval, all of those behave like lists. So you have the same performance characteristics. Okay, so let's write a small function that produces lists, multisets, and finsets to see what kind of notation we have on them. So for lists, we've seen that the empty list is written using square brackets, and we have the append operation on them. For both multisets and finsets, we have generic notation, we have the empty set, and we have the union operation, which is used to take the union of a multiset. So the union of a multiset is maybe, let's check this. What is the union of multisets 2 and 3? Yes, indeed, this works. Okay, so the union of the two multisets containing 2 and 3 is, of course, a multiset consisting of the two elements 2 and 3. So what if we take the union of 2 and 2? Then we get just 2 in the output. So the union of multisets is really it takes the maximum of the number of elements. So if the element 2 is contained once in the left-hand side and twice on the right-hand side, it's twice in the result. Okay, so here we have 3 functions that take a binary tree and return the elements as a list, as a multiset, or as a finset. So just recursive functions, you know how to do this. And then there's lots of functions that are implemented for lists, multisets, and finsets in a similar way. So there's the sum function, which returns a sum. There's product, which does the same for multiplication. There is, of course, also stuff like the bind operation, which I have for lists and multisets and finsets. So a lot of the functions exist for all of these types. Okay, and maybe just to tie into a previous chapter here. So multisets and finsets are constructed from lists using quotients. If we look at a multiset is a list where we don't care about the order, and hence it is implemented as a quotient. It's implemented as a quotient of the list setoid, and the list setoid has the equivalence relation that so two lists are equivalent if they are a permutation of each other. If you can reorder the elements, so if you can reorder the elements from the left list to get the right list. Okay, so multiset is a quotient of a list, and then a finset is a subtype of a multiset. Namely, it's a multiset where there are no duplicates. And yes, indeed, it's a structure containing a multiset and the proof that it has no duplicates.